Bonsoir, mesdames et messieurs. Je m'appelle Philippe Tortel, je suis le directeur de l'Institut des études avancées Peter Wall. On est très content de vous recevoir ici pour le Wall Exchange. Je suis ravi que vous puissiez vous joindre à nous pour participer à une soirée d'échange de vues stimulantes qui provoquera la réflexion. Good evening, ladies and gentlemen. My name is Philippe Tortel. I'm the director of the Peter Wall Institute for Advanced Studies. The Institute was founded 25 years ago to promote high-level interdisciplinary scholarship on questions of critical importance to society. One of our main goals is to bring high-level debate and discourse into the public realm, and the Wall Exchange Lecture Series was established a number of years ago to do just that. And tonight I believe that you will see a wonderful example of the kind of engagement we seek to foster at the Institute. I would like to thank first our sponsors for the evening, the Pacific Institute of Mathematical Sciences, PIMS, the Georgia Strait, and the Tyee. And of course, I would very much like to thank the band, the Straight Jackets, Jerry Bowie on trumpet, Andy Stack on guitar, Rod McDonald on bass, Johnny Boogie Seguin on drums, and our very own distinguished Peter Wall professor, Brett Finley, on saxophone and clarinet and many other instruments that he didn't bring with him tonight. The evening for tonight's presentation, rather the format for tonight's presentation will be as follows. Professor Cedric Villani will give a 40-minute presentation, and that will be followed by a question and answer period moderated by Professor Peter Klein. Professor Cedric Villani is the director of the Institut Henri Poincaré, which is France's premier and oldest institute for research in mathematical sciences. Professor Villani has received many mathematical awards, including the Fields Medal in 2010, which is often considered the most prestigious award for mathematical research. Professor Villani is a specialist of mathematical analysis applied to problems of statistical physics, geometry, and probability, and his books on gas theory and optimal transport have become classics in their field. Beyond Professor Villani's outstanding contributions to mathematical research, he has also made a huge impact on the world as the self-appointed ambassador of mathematics. He speaks with eloquence, passion, and humor on the importance of mathematics in our everyday life, and he draws inspiration from that field that he shares generously with many around the world. Peter Klein is an Emmy Award-winning journalist, and he serves as an associate professor and the director of the UBC School of Journalism. He's also the founding director of the Global Reporting Center at UBC, a nonprofit organization which is dedicated to researching and producing global journalism. Peter Klein is also an associate of the Peter Wall Institute for Advanced Studies. So I'd like you all to please help me welcome Professor Villani.
Thank you for the warm welcome. Thank you for the great introduction. It's a great pleasure to be here again in Vancouver and to be a guest of the PWIAS and to see again and meet again some old and dear friends of mine. Tonight we will talk about mathematics in a way that may not be the most usual. We'll talk about art, we'll talk about beauty, we'll talk about why mathematics is such an artistic activity, such an art. This, for many people, will seem like a mystery, but for mathematicians, for my colleagues, it is so obvious and natural that most of them won't even understand that there is need to talk about it. It looks like obvious. Let us, however, examine this in detail, and let me insist that this is just one of the many paradoxes which lie in the nature of mathematical sciences. For a start, let me review some of these paradoxes which make mathematics so special. First of all, mathematics is at the same time about rigor and imagination. A lot of rigor and a lot of imagination. You may wonder why I put this picture here on the left. This is an allusion to a classic joke, so it's a mathematician's joke, so not sure that you will find it appealing. And here goes the joke. You have these three scientists, three friends who are traveling in a distant country on a train, and here is what they see by the window. And one of them, the biologist, says, "Oh, that's funny. All my life I have seen white sheep, but I see that in this country there is a breed of black sheep." And the colleague physicist says, "Okay, let's not just do conclusions so fast. Maybe it's a random event, maybe there's some mutation, fluctuation, who knows? Some of these sheep are black, not all of them." And then the mathematician looks upon his two colleagues and says, "My friends, let us be rigorous here. The only thing we can say for sure is that in this country there is at least one sheep, such that at least one side is black." You know, rigor, rigor, rigor. And of course, it's part of this whole debate, the physicists and the mathematicians. Physicists will say to the mathematicians, "Why do you want to prove everything? There are some steps which are obvious or natural." The mathematicians say, "No, you never know. Sometimes in this obvious bit lies a lot." On the other hand, it's not the rigor that makes your career in mathematics. And when you want to hire a colleague, and if the recommendation letter arrives and says that this is a very rigorous mathematician, it's not good for the hiring. What the letter should insist on is the vision and the imagination. That is how you gain the respect among colleagues. You see this complicated formula? It's extracted from what is arguably the most famous mathematical paper of the 21st century. The final proof by Grigori Perelman of the Poincaré conjecture about possible shapes of a bounded three-dimensional universe. A beautiful piece of work solving a geometry problem of about 1 century old. And when the manuscript was out, when mathematical community could watch it and examine it, what did they say? They did not say, "Oh, Perelman managed to be more rigorous and to perform computations which are more tricky than the rest of us." No. They looked at this formula and they said, "Where the hell did he get this from? What is this? Entropy, how did he have the idea to introduce this thing? Where does it come from? What imagination?" That is how you gain the respect of your fellows in mathematics, by proving your imagination and your capacity to find the tools that people had not even conceived before. So that's one of the paradoxes. It is with logic that we prove, it is with intuition that we discover or that we invent. That is what Henri Poincaré, the famous French mathematician, used to say. A second paradox is that mathematics is at the same time abstract and universal, ubiquitous. When you say that something is abstract, it means that it's nowhere. When you say that something is universal, it means that it's everywhere. And that is mathematics. At the same time, nowhere, because did you ever see a theorem here? But at the same time, everywhere, because yes, we can say this, and that. They are all related to the same theorem or the same notion. Here I put an image which I love, Lady of Shalott. It's an allusion to a famous poetry by Lord Tennyson. And in this poem, it's about an old legend in which the Lady of Shalott is kind of princess or noble lady who has been condemned by some curse to see the world only through the reflection of a mirror. And that is the fate of the mathematicians, unable to do experiments directly, but watching and studying the world through the abstract mirror of notions, formulas, and equations, and theorems. And through this, discovering some truths. And some of these truths, even though they are abstractions, they will apply in many contexts, everywhere. Like the famous bell-shaped distribution of errors that you will find in the fluctuations of the level of the oceans or of the cosmic wave background or radio wave background, or in the fluctuations of the size of people or anywhere. One of the most ubiquitous statements in mathematics. The next paradox of mathematics is that it is at the same time very inegalitarian and very democratic. Very inegalitarian because we are not equal in front of the mathematics problem. And for most people, a researcher in mathematics is some kind of alien, you know. But for us mathematicians, when we study the achievements of the great mathematicians in the history, we feel like they are the aliens. People like Ramanujan or Gauss, we look at what they did in awe and we wonder, how could they do such things? Even if we would spend 1,000 years working on this, we would not do as great. And there is inequality thus. But at the same time, you know, mathematics problems are for everybody to try. You don't need an authorization. You don't need a funding from the government or whatever. And it happens that sometimes a great problem is solved by somebody who is an outsider, not the big shot in the field. It happens when a trio of Indian mathematicians in 2002 found a great primality algorithm, much better than what there was before for checking the primality. They were not unknown researchers, but not considered as the big stars in the field. And even more spectacularly, when just a few years ago, Yitang Zhang made an extraordinary discovery. So Yitang Zhang was not at all recognized as a hero in the field. His career had been so difficult that at times he had to serve as a waiter in restaurants and things like this. And arrived at about 60 years of age. He was not at all on the radar. And then he proved an outstanding theorem. He became a superstar overnight in the mathematics world, got all the awards that it was possible to get. These kind of things are rare, but they happen. And so there is this democratic element. The next paradox about mathematics is that it is at the same time so ancient and so new. Very ancient, because this is the only science in which we can still read the texts and contributions of scientists from hundreds of years ago or even thousands of years ago. You know, what you find in the books by Euclid is still valid. And because it's based on the truth of the reasoning, and it will always be true. And no other science can say the same. On the other hand, it's changing continuously. And there are, all the time, new tools and new objects which are being found. Here I put pictures to evoke the Ricci flow or the stochastic Loeffner evolution, which have become big stars in the past decades and have played a crucial role, for instance, in the solution of the Poincaré conjecture for the Ricci flow. So it is constantly renewing. And another paradox, which is well known to mathematicians, is that it is at the same time very solitary and very collective. Solitary because there are all these moments in which you are all alone in front of your sheet of paper and wondering how you will find the solution that for sure is hidden someplace in your brain, but that is damn difficult to get a hand on. And most of the time your attempts will end up in the bin, yes. But on the other hand, it's such a collective activity. We spend so much time in conferences and lectures and meetings and gatherings around the world. And actually, that is one of the things that these are more striking when you compare the curriculum vitae of a physicist and that of a mathematician. Usually, the physicist will publish more, but the mathematician will travel more, much more conferences and lectures. And we could spend our life traveling and discussing with each other because our job is about ideas and promoting ideas, discussing ideas, and discussion is one of the prime ways to enrich ideas. Next paradox, mathematics is at the same time so damn simple and so damn difficult. And sometimes something which looks so simple will be so difficult. Take this example, which is well known. You see, this is the problem of bisecting an angle, dissecting an angle. You have an angle which is given and you want to draw the line that will separate this angle into two halves equal. It's a simple construction. You find it in the Euclid's element. You learn how to do it. It's cool. And there is, with the compass and with the ruler, you can do it easily. Okay. And then the ancient Greeks asked, next step. We know how to divide it into two. Now let's divide it into three equal parts with compass and ruler. How do we do? What is the recipe? It took more than 2,000 years before it was proven that there is no recipe. It's not even that it was too difficult, that we had to be more clever. It was proven that there is no recipe in the world that will be able, with just compass and ruler, to separate an arbitrary angle into three parts. Now, this problem looked so simple that you would have given it as an exercise to a high school student, but actually so difficult that it needed abstract developments of higher algebra, Galois theory, and so on, to realize its impossibility. And many things are like this in mathematics. And final paradox, mathematics is both science and art. Now, we've been taught that science is one thing, art is another thing. And when you go to Vatican and you watch the beautiful frescoes by Raffaello, there is one wall about the sciences, another about the art, and another one about religion and moral. And these are three spheres which are distinct and respectful of each other and so on. But actually, mathematicians will tell you our field is both science and art. How can it be? Let's discuss about this. First, we can use art to talk about science in the same way as we can use art to talk about pretty much everything. And because everybody relates to art, it's often a good, how to say it, Trojan horse, you know, to grab the attention of people on subjects that they would not like otherwise. I remember very well when I was a kid, an animated cartoon called Donald in Math-Magic Land, a Walt Disney cartoon in which Donald Duck was having lots of adventures with about mathematical concepts. Not deep mathematics, I tell you, but I found it very fascinating as a child. And in there, the tricks to talk about mathematics in a way that would be appealing to youngsters were classical art tricks. For instance, about the golden ratio appearing in paintings, in architecture, and whatever. I will not say more about golden ratio because it is overrated, even though I'm not dismissing that it is beautiful and interesting, but we've heard about it so much, and people saw it so many times in every kind of possible trick that it's better not to add to this. You know, when mathematicians are told by their friends, oh, please tell us about the golden ratio, the reaction is, no, not the golden ratio again. Another trick which was used was about the music. And this was also one of the axes developed in Donald Duck animated cartoon. Yes, and it's good that we had music first before this talk. Music in the times of the ancient Greek was considered as a mathematical art. And this, by the way, is one of the reasons why in French language it is still plural mathematics. And what was the idea? Idea was that when we want to organize the music and the sound, we have to find the good frequencies, the good numbers, the good ratios of frequencies which correspond to the music intervals. And that the first who really took care about this is good old friend mathematician Pythagoras. And for instance, here are the numbers behind the Pythagoras scale. To go from the, Do to Sol, so Do is C, and Sol must be G. It's a quint. It corresponds to a ratio of 3/2. Or if you want, a ratio of 3/2 in the frequency, which is the same as a ratio of 2/3 with respect to the length. If you have a string vibrating and giving you a certain sound, when you divide the length by 3/2, we'll obtain the quint. And so on. If you divide by 2, you'll obtain the octave. And the problem for them was to find the good ratio so that it would be harmonious and good. This was the first attempt. Since then, there has been several other constructions involving some tricky rules in some cases. The tempered scale is entirely based on irrational numbers, something which would have sounded completely heretic to the Pythagoreans. And so there are these numbers appearing here. Let me, however, insist that it's certainly not because of these appearance of numbers that music is statistically the favorite art of mathematicians. Rather, it certainly has to do with the fact that music, like mathematics, is an abstract representation of the world and the feelings also. Also with the fact that, mathematical music is a bit like reasoning with some logical steps, some progression, some surprises and whatever. And in the fact that it's all in variations with simple elements like the various notes and the various rhythms, just like mathematics, is all about combining a number of simple ingredients together. Nice quote by Leibniz, which here I put in French. Let's say music is the pleasure of the human brain when it is counting without being aware that it is counting. Let me also note that parallels between mathematical reasonings and exercises on the one hand, and musical themes and artistic themes on the other hand, have been used by a number of authors, and maybe the one who was most successful in this, one of the heroes of my youth, I was reading his works when I was a teenager, was Douglas Hofstadter. In works like Mathémagie, this was the French title of these short stories, but also Gödel, Escher, and Bach, which was a hit in the field. Drawing parallels between structures in thoughts, in mathematics, in art, and so on. Now, let me talk about another form of art, which was very dear to me as a child, rather simple, but really taking us into what you would expect from an art. This is a magic square. What is it? You see here, it's a square grid in which you put numbers 1, 2, 3, 4, etc. And the rule of the magic square is that you should put them all in such a way that the sum in any column or any line or any diagonal will be the same. In this example, you can try it, pick up whichever line you want, and you will find that the sum is 65, I guess. And why is this interesting? Why is this useful? The answer is there is no use whatsoever. It's just for the pleasure of arranging the various elements in a way that is harmonious and surprising and beautiful, so to speak. And you know what? It's rather easy. When I lecture in schools, I teach the kids how to do it. 10-year-old kid can learn to fill a square like this as fast as writing the numbers is possible. In fact, any square whose size is an odd number. Even squares are more difficult, but the odd squares are very easy to fill. And even when you know the trick, there is a certain joy in accomplishing this recipe, a bit like a craftsman would apply the recipe to produce the artwork. Even though this recipe may be centuries old, there is a certain pleasure in applying it to organize the thing. Some people have taken this art to extremes. Okay, you may think this is a big square, but that's not what is impressive. You may, if I explain you the tricks, you will be able to fill a square of 55 by 55 if you are patient enough. That's not a problem. This square is even, that is more impressive. Even squares are much more difficult than odd squares. But this one has an amazing property, really amazing. If we raise each of the numbers to the square, to the power 2, so that the 5 on the top left will become 25 and so on, the resulting square will still be magic. That is the sum in any line, and any diagonal, any column will be the same. Now that is crazy. I mean, it's you think, look at this, and it's like these tricks, you know, in the circus, in which you put many things in equilibrium on top of each other, and so that the sense of impossibility will be part of the artistic performance. Are there some deeper connections even between mathematics and art? You see, here it's about making something which is harmonious and very surprising and so on. It looks like a beautiful game. Are there some deeper connections? The answer is yes. And one of these connections can be found in the motivations of the people and the way that they work, both the mathematical researchers and the artists. Let's hear Claude Shannon about this. Shannon is the father of information theory, one of the most creative minds of the 20th century, maybe. Here, playing with Theseus, the mice which he made, which could get out of a labyrinthum, of a maze automatically, one of the very first artificial intelligence devices. And in a text about creativity, he asked this question: what are the basic requirements to produce some good science? And there is a long discussion. He says the first requirement is obvious: training and experience and, you know, skills, etc. Then there is the idea of dissatisfaction. I mean, a constructive dissatisfaction. Now, that is interesting. We know how much dissatisfaction is important for the artists. And we hear about Beethoven or Picasso or the others. At one point or the other, they are very dissatisfied with what they've done so far. They think, I can do better, I have to reinvent my style, and so on. And that is the same with us mathematicians. If you are too much satisfied of what you've done, it's not good. Another thing I'd put down here is the pleasure in seeing net results or methods of arriving at results needed. If I've been trying to prove a mathematical theorem for a week or so and I finally find a solution, I get a big bang out of it. Now, things like emotion, passion, big bang, despair, motivation, and so on, these are words which are so important in the artistic quest and also so important in the mathematics world. And the quest for the inspiration. Shannon could have added the style. It's typical of art, we think the style, but mathematicians also know well that there is a style of this school or even that mathematician, and it's not the same as the others. The style of Shannon was extreme elegance, always very concise, to the point, no more than is needed, and beautiful, beautiful proofs. And let me quote a famous mathematical text by Alexander Grothendieck, one of the most famous mathematicians of all times, who wrote long writings, and in one of them, he talks about la métaphore de la noix. You know, the parabola, let's say the metaphor of the nut, to explain the difference between his style and the style of his fellow mathematician Jean-Pierre Serre, both of them working in the same area of mathematics, and, but very different styles. And Grothendieck said, imagine that we have a nut to open. The style of Serre would be take a hammer and bang, smash the nut. And my style would be to take the nut and put it in a sea of acid, so that it would be dissolved very slowly, the crust of the nut, without noticing anything. And yes, experts tell us that the style of Grothendieck is like everything is very incremental, from one step to another, by very tiny steps, so that you have the impression that nothing occurs. And we are really making no progress. And at the end, it's proven. There it is. The big theorem is done. These are very different styles, and the metaphor gives you an idea of the wealth of various styles that there are in mathematics. For a mathematician, it's not just the result which matters, but also the way at which you arrive at this result. Now let's talk about beauty. And let's invoke a well-known philosopher, Aristotle. Chief forms of beauty are order, commensurability, and precision. I don't know about you, but I have the impression that he's talking about mathematics when he speaks this way. And indeed, in the sequel of the text, he explains that this is the reason why mathematics is regarded as the highest form of human reasoning and the most beautiful. Let me take some time with each of these three words, order, commensurability, and precision, and develop them and why they are so meaningful in mathematics. Let's start with precision, accuracy. And let's invoke one of the superstars of mathematical history, YBC 7289. This is a clay tablet from ancient Babylonia. Maybe it's 4,000 years ago or something. And what is it? You see there is a square with diagonals, and there is some inscriptions, and this is written in cuneiform writing. And this actually is a computation of square root of 2 to great accuracy, like accuracy of 1/1,000,000th. It would be with 6 digits in our decimal notation. First, let us, respect and say hooray to the mathematicians from that time. They already had algorithms so good as to be able to compute square root of 2 with such a precision. I'm not sure in this audience how many people could do the same as these ancient mathematicians. And next, why were they doing this? There was no use whatsoever in computing square root of 2 with such a precision in those days. But maybe they had fallen in love with precision. Let's go on and refine the computation, and in the mathematics world get a value that is totally precise, much more precise than what we can do in the reality. By the way, in the honor of these ancient mathematicians, it has been called the Babylonian method, the fast algorithm which is used nowadays for the computation of square roots, for instance, in computers. Now, these were the Babylonians. Let's move forward in time and arrive at last year. The great scientific sensation of 2016, the observation of gravitational waves. At last, after decades of wondering whether it was possible, triumph of experimental science. In this case, it was the American project which got it first. There was a European project which was also on the way, but which was not as fast. Now, why is it about precision? First, because the observations were great and extremely close to the prediction. Actually, it is the accuracy between the prediction and the observation that made it that nobody contested the results. Okay, it's such a good agreement with the theory that we all believe you did observe these gravitational waves. But then what was amazing also was how tiny it was, these gravitational waves. You know, when the gravitational waves go through us, it means that lengths are distorted, but really it's tiny. Something like, at our scale, something like 1/1000th of the diameter of a proton. Can you imagine this? And still, they were able to detect it. A triumph. And it is the trace of an event that is, on the other hand, amazing in its scope and amplitude. Like the collision of two black holes, each of them more than 20 times as massive as the sun, occurring billions of years ago. Everything is crazy in this story. The amplitude, how the time scale which is involved, the length scale which is involved, everything is totally out of our world. And still in mathematics, you are able to get it with great accuracy, great precision. So this was a triumph for experimental physics, of theoretical physics, and of mathematics also for the description, by the way, wavelet theory was useful in the description and the spotting of these gravitational waves. So this was for precision. Now, order. In mathematics, you like to order things, notions and objects and so on. There are so many examples of this. Let me describe one of these many, many examples, bringing order to the world of the polyhedra. Here are some polyhedra. You have variety of shapes and whatever. Polyhedra, they have vertices, they have faces, and they have, gosh, I forgot how you say it in English. Arrête. Edges, thank you. And by the way, I put the French initials, but I should have put for this talk the English initials. So S is for sommet, these are the vertices. A is for arête, these are the edges. F is for faces. And here is the recipe, which sometimes is called the Euler formula. You take any polyhedron and you compute the number of vertices minus the number of edges plus the number of faces, and you will obtain a result that only depends on the global shape of that polyhedron. For instance, without doing any computation, I know that for the 3 polyhedra on top, the result will be 2. Because these are something like, start from a sphere and then with a hammer, transform it a little bit, and we know it will always be 2. Not so for the 2 on the bottom. These 2 have a hole. You could put a string in between. You can wear it as a necklace. There is one hole. For this reason, if you do the same computation, you will obtain 0. So we see here how we can bring order in this polyhedra and quantify the things such as the global shape. And then you can classify the polyhedra according to their shapes. There is also an analog in the world of smooth surfaces, not with edges, not with vertices, but very soft, and so on. This is called the Gauss-Bonnet formula. The previous one can be thought as a particular case of this one. Mathematicians will read this as follows. You consider the total integral of the curvature along your closed surface, and it will always be a multiple of 2 pi. 2 pi multiplied by some integer number. Which number? For instance, with the shapes on the top, because there are 2 holes, this number will always be -1. For the shapes on the bottom, because they have all one whole, this number will always be 0. So that total integral will be equal to 0. And again, that's one basic way to put order among all these shapes, one of the bases of topology. Now, let's talk about commensurability, the third one. Commensurability, you can think about it in several ways. You can think of it in terms of various numbers which you compare to each other, maybe 2 and 3, and then we are back to these problems, for instance, in the construction of the scale. But you can also think of it as concepts which can be matched together. One idea that is comparable to another idea. Or some mathematical objects which come together. And here comes another Euler formula, which many people consider as the most beautiful that there ever was. Actually, there has been a series of experiments conducted by researchers in cognitive sciences. And they have looked at the brain of mathematicians when they are presented formulas, and they measured the level of pleasure which was expressed in the brain. And they found that this formula was the one that triggered the highest level of pleasure in the brain of mathematicians. So that it is proven to be the most beautiful in some sense. So what does this formula say? It shows exponential I pi plus 1 equals 0. And what is beautiful about it is that it puts together the 5 most emblematic numbers in mathematics. First 1, which is the basis of everything, but then 0, which was a great invention, which we learned from our Indian friends, and which was instrumental in making operations systematic. But then also pi, the symbol of geometry, but also E, the basis of the exponential, symbol of everything that is growing, be it in population dynamics or in economy and so on. And finally, I, the imaginary number, such that the square is equal to -1, which was introduced to solve algebraic equations and the symbol of solving equations. And all these 5 numbers, which were invented or discovered at various epochs for various purposes, finally are all linked together through the basic operations: equality, plus, multiplication between the I and the pi, exponentiation between E and I pi. So the 5 basic operations, the 5 most important numbers, and you get them all together. That is what mathematicians will call beautiful, because it's surprising, because there is harmony, and it is as if it had been planned this way forever. Henri Poincaré told in the same idea, same order of ideas, he told of the profound beauty coming from the harmonious order between elements and that pure intelligence can grasp. Not a beauty which you appreciate through your senses, but which you appreciate through the brain and thinking. Now, at this point, many in the audience will tell me, now, Professor Villani, that is good, but beauty and so on, it doesn't look very much like my courses of mathematics when I was at school. And that is indeed a problem and an enormous misunderstanding. There is a well-known pamphlet which was written about this by mathematician and writer Paul Lockhart. The title is A Mathematician's Lament. Lamenting about this deep misunderstanding about the status of mathematics, which has it being hated by the majority of population. And what Lockhart tells us is the first thing to understand that mathematics is an art. He says the first thing to understand. There is such breathtaking depth and heartbreaking beauty in this ancient art form. how ironic that people dismiss mathematics as the antithesis of creativity. They are missing out on an art form older than any book, more profound than any poem, and more abstract than any abstract. And Lockhart tries to understand where the misunderstanding comes from, and he's very clear. It is school that has done this. Now, don't mistake him. He doesn't blame school teachers. He blames the school system in which it is all about feeding kids with the technique and the operations and how to solve this problem and that problem and that problem and the recipes. And he says, let's make a comparison. Imagine that you would teach music to our kids in a way that they would learn the logic of the scale, and they would learn how to write a score, and they would learn how to draw beautiful notes on the score, but they would never hear any music. Or let's imagine that they would teach art in such a way that you will first learn about all the various shades of color and the various numbers that you attribute to these various shades. The blue is this code and the green is this code. And all the kinds of paint brushes and how you will put the paint on the paintbrush and the paintbrush on the paper. But you would never draw anything. And that gives you an idea of the teaching of mathematics viewed from the mathematician's point of view. Insisting on the technique and forgetting about the goal, which is about creating new forms of intelligence, about finding new truths, and so on. And is there possibility to touch this beauty even at elementary level? The answer, again, is yes. And it's one of the goals when we teach mathematics to always put together the technique and the appreciation for the art. For instance, one of these stories which takes us back with Carl Friedrich Gauss is the story of young Gauss at school. It's a story I remember. It was already in one of the books of popularization of mathematics that I was reading as a kid. Let's tell it again. So, according to the story, young Gauss in school, elementary school, one day was given the problem, the teacher was giving the whole class the stupid problem of adding all numbers from 1 to 100. You know, let's train ourselves for good addition. 1 plus 2 is 3, 2 plus 3 plus 3 is 6, etc. But Gauss did not do it dumbly. He thought about it. After a second, he wrote the result and took it to the schoolmaster. How had he done it? I thought, let's do it in an intelligent way. Okay, we can do this sum in any order. It will be the same result if we start from the end. 100 plus 99 plus 98, etc. All the way up to 1. Okay. And if I write these two sequences of additions like this, and then I do the summation of this all vertically. 1 plus 100 will be 101. 2 plus 99 will be 101, etc. And I will be counting 100 times 101, which now is not an addition but a multiplication, whose result is obvious. Just adding 2 zeros gives us 10,100. Now, this is what I obtained by adding all these numbers, but each was counted twice. So I should divide by 2, and that is the final result that the master wants. 5,050. Now this presents all the characteristics of a beautiful reasoning. First, you can see that it is short, elegant. You know, I don't have to go through all the additions. I have the result after a short time. It's effective. It can be generalized. With this method, I do much less, there is much less risk of mistake than if I do all the additions. But also, I can, in 1 second, do the same thing for adding numbers from 1 to 1,000, for instance. But also, in the way the reasoning goes, there is this notion of commensurability. one argument after the other. First we reverse the order, then we do these partial sums. It's not, since it's a repeated sum, it's actually a multiplication, and then we divide by 2. And the important topping, you know, we say cerise sur le gâteau. I don't know if there is the same in English, the cherry on the, sorry? Cherry on the cake, good. And it's surprising. Like, why on earth are we counting them backwards? At first you don't understand why there is this. That's where the imagination comes from. And that's where there is an element of beauty. Let me say that this beauty, you can find it at all levels. From such a simple problem that it is a school-type level to the most difficult and emblematic problems of mathematics. Let me actually skip the discussion for this one to concentrate on the rest, but the most famous problem in mathematics is the Riemann hypothesis. And why are people so concerned about it? Why is it so famous? The best answer is that it is so damn beautiful and related to many other topics in a way that also would be extraordinarily beautiful. And that one is not a simple school child problem. It's one that has been a challenge for the imagination of mathematicians for 1 century and a half. Okay. Yes, let's skip the Riemann hypothesis here, and let's now share with you a memory of my mathematical career to insist on how the notion of beauty is also a guide. So this is an extract of a paper which is dear to me. Actually, I think is of the papers that I published and the theorem that I proved is the first one that I am proud of. You know, when you write your first research article, it's such a big fuss and you are so proud of it. But years later, when you look back, you think, oh, that was not so good, actually. But this one, when I look back, I think, oh, that was not bad, actually. So this was 1997. I was a PhD student. And I was visiting Giuseppe Toscani, a specialist of Boltzmann equation, in Pavia. I had met Toscani a couple of months before in a conference in France. I had shown him that there was a big mistake in one of his papers, which is a very good way to become friends. And Toscani had invited me to come over and visit him in Pavia, and he told me, you know, I have this crazy idea for solving the Cecchiniani conjecture about the Boltzmann entropy production. It's a crazy idea, and so on. And so he explained me, you do this, you perturb in this way, go to the limit, etc., see what remains. He was director of his lab, so swamped with administrative duties, and so he had no time to check even his own idea. But I was a PhD student with all the time in the world, so I sat down and did all the computations and reasoning to try the idea. And after I tried, I discovered that the idea was not only crazy, but in some sense stupid. There was no way that it could work, no way. But in the course of trying, there was something that popped out in the computations. And putting together various terms, it was recombining in a kind of miraculous way into a perfect square, beautiful square. And I thought, that is cool. That is too beautiful to be useless. And actually, this was the start of the solution. Spotting the small miracle, the harmonious identity, was the key to the sequel. You know, in mathematics, there are so many paths you could try to go. You need something to guide you. And often that something is the aesthetics. Where it is beautiful, we bet often that that is the direction that we have to dig in. Because where there is beauty, there is more chance that it will be truth. After all, as Sofia Kovalevskaya, the great Russian mathematician, said it, nobody can be a mathematician without the soul of a poet. Now, let's take on this and talk about poetry. And again, mathematics and poetry, you'd think that is the opposite, but quite not true. Mathematics is the poetry of science is the title of a lecture which I was giving a few years ago in Belgium. It's actually a quote from the former president of Senegal, Léopold Senghor. Les mathématiques sont la poésie des sciences. See, on this, this was the poster prepared by Étienne Lécroard, a very gifted drawer of crazy comics with all kinds of logical rules. On it you can see the mathematician getting on top of the elementary operations to reach for the infinity, to reach for something that is hidden. And a lot of poetry is about displaying something which is invisible and reaching for it. What can we say about the relations between mathematics and poetry? First, we can say that mathematicians, like poets, believe very much in the power of words, of concepts, and of everything that there is behind. When a poet uses a word, it's not just the bare signification of the word, it's the whole set of images and contexts that there will be within this. And when a mathematician uses a concept, it's not just a definition, it's the whole theories that lie behind, that has been transformed and repeated and so on. And finding the right notions for mathematicians is so damn important, and playing with them, and these notions were something that is not present initially in the problem, but that will be crucial for the solution. Playing with infinity. What is infinity? Infinity does not exist in the real world. But introducing the infinity and playing with it and handling it in a clever way is the key to many problems of mathematics. Integral. Integral is notation that was invented by Leibniz. But then it was redefined, rediscovered. And when you write integral, there's a whole bunch of theories and reflexes and contexts which goes into the mind of a mathematician. There are other relations between mathematics and poetry. First, the role of constraint. Poetry, in most cultures around the world, is the most constrained art form, with rules of the number of syllables, of the sounds, whatever, which words you're allowed to use. And similarly, the mathematical writing is extremely constrained by the rules of logic and presentation. And in both, as a counterpoint to these constraints is the imagination and how important it is. And we can also say maybe the most important of all, poetry is about creation. That is even the etymology of it. About creating a new world, invoking it. And that is what mathematics does. Create a world which is a reflection of our world, with rules that are inspired from our world, but which we can tweak and change. And we can use mathematical shapes and concepts and functions to reproduce the world around us, to recognize some patterns, some abstractions in the reality around us. And we can go much further. We can represent and design things even before they exist, or things that will never exist. Look at this crazy building, the Fondation Louis Vuitton in Paris. Before, yes, by American-Canadian architect Frank Gehry. Before you construct such a thing, you'd better first create it in the mathematical world. Otherwise, there is a good chance that it will collapse soon after it is there. And it's a very important step to use sophisticated software to simulate all the, the stresses and the strains in the building and make sure that it will be functional. And when you do this, you create something which does not exist yet, but it's a full creation in the virtual world. And it will help the creation of the artists. Look at this. This is an image from a famous movie in the recent years, Gravity. Oscars, whatever, fame, a lot of success. Everything is fake in this movie, or almost everything. Well, the face of the actress is true. But then All the rest is created with computations and algorithms and mathematics. And it looks so true, except that the rules have been changed by suppressing the gravity. We could equally reinforce it, do whatever we wish. And this is possible in this mathematical world which we recreate, which is a reflection of our world, but in which we can change things. This leads us to the fact that nowadays the movie industry very much relies, at least it's a strong component, the mathematical recipes and modern image processing has been developed by visionary people who were at the intersection of science and art, like Edwin Catmull. It has been implemented in emblematic movies like Toy Story by emblematic studios. When you see in Brave the motion of the hair of the heroine, it's based on models of physics powered with mathematical equations. It's not realistic. It's better than reality. It's a world in which hair obeys some physics rules which make it even more elegant than in the real life. You see, it's poetry. And there is research going on in this respect. Here is an evocation of some work by Marie-Paul Cany, one of the leading experts in this, about how to create universes in the digital world, the graphic universes. Here, what it would look like to have some, digital clay on which you could use to play with it and make the shapes and distort them and so on. And a few years ago, Hollywood attributed a tech Oscar to researcher Markus Gross from ETH Zurich for a new creation, a new algorithm, so-called wavelet turbulence, which could be used in special effects to create fumes or flames which obey certain movements, as you can see in these two examples created by the studio One More in Paris. I remember a few years ago a big conference in San Diego in which there was a session about movie industry, and one expert, research head of a big Hollywood major, was telling us, we should pay you guys royalties for every blockbuster in Hollywood. Of course, we did not object. Let me tell you that behind these creations in the world and in the movies and so on, play a crucial role some models from mathematics which are used to describe phenomena around us. Partial differential equations, actually the field in which I was trained, these equations which have been developed in mathematics, in physics, to model all kinds of phenomena around us, like waves, fluids, gases, galaxies, plasmas, the cosmos, atoms, finance, biology, whatever. All these phenomena, all these things, first had to be put in equations that would describe the reality before being used to modify the reality and create it as we wish. And so all this is about poetry in some sense. Okay, now I've told you about beauty, poetry, art, and so on within the mathematics. And some of you will feel, okay, that's very good, but still we are missing something. Can we use mathematics to create art? And if I am an artist, can I find some inspiration in mathematics? The answer is yes. And to conclude this lecture, I will show you some examples of real art that is inspired by mathematics, either directly or indirectly. And I will argue that all these examples fall into three categories. three different connections between the art and the math. The first category is when you have some mathematical recipe that will produce or help producing a work of art. A famous example is fractal theory. Fractals are these shapes based on simple geometric recipes which appear to be interesting at all scales, and it's such that the part looks like the whole in some sense. So that when we zoom, it looks like the whole picture. They are not based on complicated formulas. Usually the recipe is rather simple to state, but they are complicated objects. Let me show you a recipe to construct a fractal image. There are various recipes. I will not show you the simplest one, but one that gives rise to spectacular fractals, and the so-called Newton method fractal. So it will be a bit more advanced than the rest of the talk, but relax. Even if you don't understand all details, it will be all right. So it deals with complex numbers. Complex numbers have a real part and an imaginary part, and you should think of them as points in the plane rather than on just a line. Now, let's consider a polynomial. X is the variable, and this polynomial p will be x squared plus 1 multiplied by x minus a. It's a polynomial of degree 3. A will be any complex number. Let's take 1 and write this polynomial. Now, we may ask when we can solve this equation of this polynomial being equal to 0, that is finding the root of the polynomial. One root is a, obviously, because when x equals a, the whole vanishes. But also there are two other roots, which are I and minus I, where I is such that I squared is equal to minus 1. Now, starting from another point, another complex number, I apply a recipe which is known as the Newton method to find the roots of an equation. It's actually a generalization of the Babylonian algorithm that I was talking about. Here is the formula, and don't worry about details if you're not comfortable with them, but starting from a first approximation, you construct another one which will be more precise through this formula. From the approximation Zn comes the next one, which is Zn plus 1, and then the next one, and the next one, and the recipe, if everything goes right, will converge to one of these roots, either a, or I, or minus I, depending where you started from. Start from a over 3. That is your first approximation. And go on. Apply the method. Maybe it will converge to a, maybe to I, maybe to minus I. You have to run it to know. And then if it converges to a, you will color a green color. If it converges to I, you will color a into cyan. And to minus I, you will color it a deeper blue. Okay, that is the rule. And with this, we will create a work of art just by coloring the points A according to this rule in one of these 3 colors. That is what Michael Hartley did for the project which I will show you in a moment. For every point A, you look where the method takes you and you will color the point accordingly. And this will produce a fractal. You will see in the fractal, you see these 3 colors that I mentioned, the green and the 2 shades of blue. And also, you will see some elements in black. In black, it is when the method does not converge. And also various shades of these colors depending on the speed at which the method converges. And we will zoom to see the fine details, and as we zoom, we will slowly change the scale of colors just by shifting a bit on the numbers of the colors. So these are very mathematical rules, and let's see what we obtain. When we go closer, it looks more complicated than it was. it looks like imagination, but it's just the result of that single mathematical rule which I gave. See these kind of things which occur here and there, they look like Mandelbrot sets for those who know, but they are not exactly. They will come here and there. Look at these shades now, it's a completely different figure. Maybe inspiration from electricity or from gardening, who knows? Look at this, it's again changing, but it's still the same mathematical rule as from the beginning. And again, these strange shapes keep on coming again and again. It's really a fractal type structure. Well, we could continue forever, but we have to, go on quickly. Let us briefly talk of other mathematical rules which have been used by artists. Quasi-periodicity, which is not periodic really, but some kind of were used by artists in Persia already hundreds of years ago, long before it was found that these structures also exist in nature. Antoni Gaudi in Barcelona, for some of his arcs, liked to use the shape which comes from physics. The chaînette, we call it in French, I guess, catenary or something. This is the shape of this, when you have a chain which lies under just the action of gravity. And Gaudi found them beautiful. He watched them in mirrors to reverse them and use them to make these arcs. He used to say that he was taking the inspiration in the shapes of nature, which, as we know, since Galileo, are themselves written in the language of mathematics. Xenakis used dynamical systems and chaos to produce some music. Raymond Queneau, member of a French group called Oulipo, who was fascinated in mathematics, also used combinatorics in this strange creation. You see, all the each band has one line. You can combine them however you wish to create a poem, and in this way you create, as he says, 100,000 billions of poems. It's a way to put the combinatorics in your art. György Ligeti, who was also fascinated by mathematics, made some pieces of music with crazy constraints, very logical. In this one of the Musica Ricercata, the constraint is simple, only written with A's. You would think that must be the most boring piece in the world. But no, not at all, not boring at all. Okay. First of all, actually, there is one D at the very end of the piece. But more importantly, there are all kinds of variations in the rhythm, in the strength, etc. And it does work. Now, these are examples in which the mathematics was used to produce or to participate in the production of artwork. Now, for another possibility, another possible link, is when mathematics provide an inspiration. You don't apply the formulas, but you think of the mathematical theory and this inspires you for work of art. For instance, by mathematician and artist Anatoly Fomenko, this kind of dreamy picture of probability. Or for instance, this artwork by Escher, relativity. No formula about relativity has been used to create this, but it's like dreaming about the notion of changing point of view, changing the referential, which is at the basis of the relativity. Or, for instance, again by Ligeti, a very difficult study called Désordre, like chaos, which has some inspiration from the theory of deterministic chaos. It's at the same time very regular, you see, the rhythm is always the same, and very irregular in particular through these accents, which occur at kind of unpredictable times and which create a whole impression of chaos. Sometimes the inspiration can build on sophisticated theories. Here is Bill Thurston, one of the great mathematicians one of the great geometers of the second half of 20th century. And one of his best claims to fame was his work on three-dimensional geometry and topology. Beautiful book which was proposing a classification, an ordering on all kinds of geometries, all kinds of possible geometries, and actually paved the way to the solution of the Poincaré conjecture. And one day, the Japanese designer Issei Miyake heard about this work, found about it, and decided that he would make a collection of high fashion based on the work of Thurston, inspired by the knots which Thurston used for representing the possible geometries. Again, no mathematical equation was used to produce this, but it was inspired from it and from the shapes. And this was presented, of course, in Paris, in the Louvre, and this was called the Poincaré collection of fashion. And now there is a third way, which is not about inspiration or about using mathematics, but which is about representing mathematics, putting it in scene. This is the approach which was used by the surrealist artists in the 1930s when they came to visit my dear Institut Henri Poincaré. They found this kind of figures, these shapes, with these surfaces which are used to represent and illustrate theorems. They had no idea what this meant, but they found it beautiful. These works done by the hand of humans to exchange ideas from human to human, they found it fascinating and they wanted to pay tribute. They photographed it. We know that they didn't understand the least of it because in one case they photographed the support instead of photographing the shape itself. And look, they put it like in scene. This doesn't look like a mathematical picture. It looks like a cat, maybe, or a mask. Man Ray, who was the photographer here, called these the Shakespearean equations. Here is another example in which somehow the mathematical lines for the rules of perspective are the artwork and what attracts the look. Again, in the idea of representing without understanding, there are these poetries, songs of Maldoror by Lautréamont, in which mathematical words are inserted within the poetry as a tribute to the mystery that they contain. Okay, on a lighter note, the singer Évariste, one of the very rare pop singers to have made a postdoc in Princeton University, did these crazy songs with mathematical vocabulary inside. This is one of my favorite examples. This equation, for sure, there are some around you who have passed very nearby without noticing. This is a Schrödinger equation, one of the pillars of mathematical physics in the quantum world, and it is represented in a sculpture which is on display in the center of the Paris subway, Châtelet-Les Halles station. I find it very ironic, by the way, that every day hundreds of thousands of people probably go nearby this sculpture, and I would bet none of them notices that there is the Schrödinger equation in there. As a metaphor of the fact that we are surrounded by equations and we don't notice. And the final example, again for representation, will be that I will present to you is by Jean-Michel Alberola, contemporary artist. He wanted to represent the magic of transmission of the mathematical ideas. What happens when we talk to each other in the mathematical world and explain a mathematical result. And so he portrayed the mathematician, and it was me on this occasion, talking about a mathematical result. In this case, it will be the one that I explained you, that I started with Giuseppe Toscani on the Cerciniani conjecture, and just filming it, putting it in film without understanding anything, but to invite the viewer to focus on the magic of the mathematical writing and how the ideas are transmitted, and even the details, the chalk, the blackboard, and so on. So let's go for it. Oh, by the way, it's 21st century, and we never found anything better than blackboard and chalk to transmit mathematical ideas. It really is the best. It adapts to the motions of the brain. You can improvise, modify, and there's this beauty of the integrals or whatever signs. Admire the little dust of chalk which gets out from time to time. Yes, from time to time there are mistakes that you have to repair. Yes, and the chalk gets broken more than once. And continue one bit of reasoning and the other bit, and let's put together and write it here, and here's the assumption, here's the conclusion, etc. And all this translates in the brain of the viewer into ideas and some impression, sometimes confused, sometimes very clear, and so on. Oh, this is a dramatic moment. And some parts of the blackboard are kind of in the dark, some parts are kind of lit. Maybe a metaphor of the fact that some parts are obscure and some parts are bright in the reasoning. And in the end, you have this result. Now, for the mathematician, this is a working device. You know, it's part of our job. But for the artist, it's a piece of art. It's something that the artist will choose to communicate to a broader audience as a testimony, and as to invite other people, non-specialists like him, to marvel about these miracles. Transmission of ideas through language, through the writing, through the mathematical formalism. A piece of art. Thank you for your attention.
So it must be a mathematical formula for putting this. Thank you. On behalf of everyone here, particularly those of us who are not professional mathematicians, I want to thank you, first of all, for being the ambassador for us, and also for, clearly in this presentation, not underestimating the public's interest and capacity for understanding complex issues. So I want to thank you for that. We're going to have about a half hour, just under a half hour for questions. If you can, there'll be some positions for microphones. We could start lining up as soon as they get lit up. And if you'd like to send some questions in through Peter Wall Institute's social media, the addresses are up there. And we'll try to get through as many questions as possible while we're waiting for some people to line up. Maybe I'll start with first question. Henri Poincaré, the namesake of the institute that you run and who you referenced a number of times, is often said to be the last mathematician to have mastered the whole of mathematics. Math has become so complex, so specialized, and is that a good thing in your mind? Is it a bad thing? Is that perhaps one reason that, in the time of Aristotle and many of the great thinkers, Da Vinci, math was part of a general intelligence of an artist, of a philosopher, of a poet. Today it's not. Is that because of the specialization, or at least partly because of that?
I think there are several trends. First, specialization has made it impossible for a mathematician nowadays to comprehend the whole of mathematics. And there has never been another Poincaré, and there will never be, in the sense that we will never see another mathematician mastering the whole. Except maybe if one day artificial intelligence manages to make superhuman mathematicians, but we are not nearly there. This in itself is neither a good nor a bad thing. It's a thing. I mean, it's unavoidable. In all fields of human knowledge, there is more and more material, more and more diversification and specialization. We have to be aware that it has to change the habits of working. It implies more collaborations because it's more important than before to put together expertise of various people. It requires also some mechanisms for more travel, more discussions, more meeting, because the specialized knowledge which is not in your realm will not come spontaneously to you if you just you cannot just get it from your reading and your studies. It requires also more curiosity. You have to be on the watch out about what other fields are doing, and even if you don't understand precisely, keep an ear open about what is going on in there. That is for the specialists. Now for the more broader audience, and yes, why are the physicists in their philosophers or in their majority not aware of sophisticated mathematical arguments? And the answer is also yes. Nowadays, to study the philosophy in itself is a huge amount of time to invest. To study the mathematics also is a huge time, and so on. And you cannot do everything at the same time. I would say that it is then the same. It requires more collaboration and dialogue. If a philosopher wants to incorporate mathematics in his or her thought and works, it cannot be by just personal work. It has to be through dialogue with some specialists also.
I want to encourage the audience members to please come to the mic. This is an incredible opportunity to get to ask one of the leading mathematicians in the world some questions. Try not to make your questions too technical, and try to keep them short because we are short on time. I'll ask one more question that may be relevant to. I suspect there may be a few math teachers in the audience. I'm a former math teacher, and I was particularly struck by the notion that the math teacher you showed up there from St. Anne's School in Brooklyn has written about how math is taught so poorly, that it kills the curiosity and the beauty and the artistry for so many young people. Some are drawn to it, the most talented perhaps amongst them, and pursue it, but for so many people, I mean, how often do you hear math is hard? I never liked math. It was always my hardest subject. What can we do? What can teachers do? What can we do as a society to make teaching math better and more accessible to a broader range of young people?
Now, that is a tricky question. It's not one that has a simple answer. And very important is to find a balance between, let's say, the technique and the rest. And the rest will be the engaging activities, the games, the stories, the riddles, the marveling, the beauty, whatever, the art in all kinds of components. And one has to find a balance. It would be a mistake to believe that you can do it entirely in dreams and games and stories. It would be a mistake to believe that you can do it entirely in that way. In the same way as in a music school, you don't just listen to music and marvel about beauty and art. You also have to learn the technique. But you have to find the right balance between the two.
All right, let's turn to a question here.
First off, I'd like to thank you for such a wonderful presentation.
You just get a little closer, I think.
I'd like to thank you first off for such a wonderful presentation this evening. It was an experience that I'm very happy to be part of. How much of a barrier would you find language when it comes to trying to communicate your ideas to people that maybe speak different languages? Would you need interpreters? Would you need to just use mathematics and numbers in itself?
There is no serious language barrier in mathematics because the communication is mainly at the level of putting the concepts together, and even if sometimes it's by using approximation about the words or repeating or doing it in a very inelegant way or by borrowing words from one language or another, the concepts you can always go through. It may not be elegant, it may not be so efficient, but it will always go through. You know, even though mathematics can be described as a language, it's not a language of the same nature as language in which we speak. And new cognitive sciences have shown that it's not the same part of the brain which we use when we read a text or understand a text in spoken language, or when we understand a mathematical statement. Mathematical thinking is mainly non-verbal. So we use the language as a way to convey the idea, but then we forget about that conveyor. It's the arrangement of the ideas that counts.
Thank you very much.
I have a question of the role of computers have now in research in mathematics. We've seen a lot of the application of computers in animation and whatnot, but as a statistician, I couldn't see a day without me using my computer, and every now and then, when I'm looking at things the computer is doing, it's like there might be some interesting theory here that I need to work out a proof or something. But I have seen that, especially among mathematicians, kind of like, oh, it's a bit of a dirty situation, relying on computers to discover mathematics. So I was wondering, in your comments, it says, like a valid form of knowledge, or like anything can be derived from the abstract?
There is a whole thing, of course, computers and the influence of computers on mathematics and vice versa would require a whole discussion with many interesting examples. First, computers have made it possible to do mathematics, check mathematics, guess mathematics without having a regular proof. And by the way, a computer, to some extent, is a device that is able of performing any mathematical calculation. And then status is uncertain and depends very much from subject to subject. Sometimes you have a statement that you observe in the computer world, but can be mathematically disproved. Sometimes it's the contrary. You have a mathematical proof, but you will not observe it in computer in practice because computation time would be too large, or because it's an effect that you would only observe after a very long time, or things like this. But in many cases, computers have had a good, strong, positive influence in suggesting new ways, in suggesting statements, in guiding intuition, also in helping proofs. So far, there has been no serious mathematical theorem which has been proven automatically by a computer. But there have been examples in which part of the proof was based on computer action. There have been examples in which checking of complex proofs have been made through computer. It's clear that checking proof is much easier than making a proof. And there are some impressive experiments in this respect. Also, computer science for sure has influenced the style of mathematics. And the fact that we now value more, constructive proofs than before, more algorithmical proofs in their writing and structure is for sure also influenced by the culture of computer sciences. So there are these influences at all levels, at the level of what we regard as a proof statement or a true statement, as an interesting statement or as a conjecture, but also in the structure and the style of the proof. It has influenced in all kinds of ways.
Thank you.
Let's go to a question over there.
First, thank you very much for the beautiful and inspiring lecture. And my question is, to what extent do you think humans discover mathematics versus invent mathematics?
Now, that is a tricky question. And it's amazing to see also how much this question is important to people and fascinating to many people, even hundreds of years after the debate somehow was formulated. It is constantly being refueled, this kind of debate. And mathematics, human construction, or mathematics engraved in the reality and in the universe and discovered by humans is an ongoing debate on which there are fashion effects. I mean, depending on the general context and the period, you will find different answers. I belong in those who believe in the mathematics being discovered, and I think we are the majority nowadays. But a few decades ago, we were a minority, and there was a different feeling about it. Why? You know, sometimes visions of the world change. I tend to believe that a few decades ago, mankind still had the kind of illusion that it was possible to control the world and to master the world, and that now it's bitter disillusion when we see subjects such as climate change, uncontrolled economy around the world, uncontrolled politics around the world, whatever, the impression on the country that we don't master anything. And even though there is no logical relation between these human affairs and the status of mathematics, I think this also influences us, that maybe we are more humble. After all, it's an illusion to think that we can control things, and we mainly witness or discover or see the things as they are.
I'm going to go to a question that came in from social media. You talked briefly about how mathematicians, parts of their brains are stimulated by certain things. You gave the Euler identity as one that's objectively seen as most beautiful because it's most stimulating. So we have a question about what does a eureka moment feel like when you're solving a problem, and do you have a particular one that's particularly memorable?
I have some of them which were memorable, and I talked about in my book. But this is not a shameful advertisement for the book, of course. And
it's a very good book. You should get it.
And we all have, in research, these eureka moments. Some of them big, some of them small. It feels like wow. It feels like sudden, often. André Weil famously compared it to sexual pleasure, adding that it was, in a way, even better than the sexual pleasure because it lasts longer, you know, like you think about it and wow, it's a wow that continues, the amazement in front of the beauty of the arrangement of the reasoning and the mathematical argument. Let me share with you one of these stories, again related with still the same problem I was talking about, and the entropy production and that work I did with Toscani. At one point, a few lectures after that, I was giving a series of lectures in Collège de France in Paris as part of an award. And in those days, I was living in Lyon. And so once a week, I would go to Paris to give my lecture. And in one of these occasions, I explained the work that we did with Toscani, and should we do this and this and that and that. And one of the people in the audience, a colleague, said, but don't you think you can improve for this? And no, we tried, cannot improve. He said, but still, no. Okay. But on the train back from Paris to Lyon, I started thinking, yes, after all, am I sure that we cannot improve? And then, but yes, we can improve. And we can do this and this. And all the way during the train, I found that's good and beautiful. And you know what? Next week, I'm going to tell them, as a compliment to the lecture of this week, that we can indeed improve it significantly. Okay, then a few days pass by, and I'm very proud of this, and I have written how I have this much better result now. And, just a day or a day and a half before the next lecture, I discovered that there is a big mistake in my reasoning. It doesn't work, just doesn't work. And no, but it's so beautiful. I have to show them. I have to fix the proof and show, and try all the evening and the night and so on. And on the last, just before it is the time to go again, it still doesn't work. Wake up in the morning like, how do? I have to fix this proof, this time proof, but this, no, doesn't work. Take your breakfast like a robot, thinking, how am I doing it, and how and so on. Go on the train station, how am I going to do it? Arrive at the train, what I'm going to sell them. And go on the train and so on, and then sit down, and then, now I know. And the instant that I sat down, I knew how to do it. And I spent the 2 hours of train between Lyon and Paris to write down that argument. Now it was neat, perfect, and I presented it when I arrived. Here is the proof to improve it, etc. Yes, these are some experience that you remember, Yuri.
Unfortunately, we only have about 5 minutes left, so I know we have a number of people who have questions. I think we're just going to take maybe 2 more questions. So we'll take one here and one there, and I'm sorry the rest of you, we're not going to be able to get to your questions. Professor Villani will be at the Pacific Institute for the Mathematical Sciences on Thursday, so if you'd like to continue discussing math with him, you can, but we'll turn here.
Thanks for an awesome talk. I really enjoyed just imagining all the different relationships in the mathematics. And I was wondering what you kind of think of between mathematics and art. You kind of came from math towards art and compared it that way, but how would you see mathematics from the lens of art? And are they equivalent? Are they converging? Are they parent-child relationship? What is that relationship?
Now, this is an interesting question about, yes, we went one way from one to the other, from the math, find art in the math. But can we do the reverse? Can we find math in the art? Can we use artistic lenses to inspire mathematics, for instance? There are some things like this, but so far it has remained a few curiosities, some anecdotes, and nothing to a comparable scale. I mean, the fact that there is an artistic side in mathematics is in every day in the conversations in mathematics lab. But seeing math in the art is much more rare. Now, some people would say still that there is something. I have regular collaboration with artists, graphic artists. We published one comics together, and we're working on second one. And he likes to say that there is a good dose of mathematics in a way, in the way that you prepare drawing. The composition, you have to take care about the balance of the various ingredients. There is some logic, something goes there, then something else has to go there, and so on. And even when you're not good at mathematics, you can become very expert in this kind of mathematics of the composition, so to speak. Also, at a more elementary level, we may say that some notions emerged in art and in mathematics quite parallel and strong ways. For instance, symmetry has been a favorite of art ever since the start, and we may argue that it's a mathematical notion which was inspired by art in some sense.
Thanks.
Professor Villani, that was a very entertaining and inspiring talk, so thank you. My question is, how do you nurture your creativity?
Creativity requires lots of ingredients, and there is never a sure recipe for them. And of course, this is the biggest problem or fear for creative thinkers, be it in the field of research or art or whatever. How am I sure that I will continue to have good ideas? There's no sure recipe. But some things are favorable. Constant or frequent discussions, being exposed to a number of ideas, having a good access to what other people have done, because new ideas are often inspired by previous ideas. It is good also, there is something very much about the atmosphere, the environment. Creativity is often a group action, a collective thing. And you can think of, when we talk about creative things, creative laboratories, creative cities. And it's as important as to talk about creative individuals. So it's all a very ecosystemic problematic, creativity. Also, creativity needs constraints. And that's something that the artists know very well, and one reason why they sometimes impose constraints on themselves. Without the constraints, you don't have the motivation to break them, to circumvent them. And sometimes some of the most creative discoveries are also based on the constraints. And by the way, one of the reasons that math has been such a creative activity is that it is so damn constrained by the rules of logic.
Great. Well, thank you. Thank you for your beautiful
Thank
talk.
you.
So this brings to a close our Spring 2017 Wall Exchange Lecture. I would like to thank very much Professor Villani for a wonderful and inspirational talk, and Professor Klein for moderating an engaging question and answer period. I would like to thank again our sponsors for this event, the staff at the Vogue Theatre and our wonderful house band. And of course, I would like to thank all of you for coming out tonight and being part of this conversation. I hope that you take the ideas of passion and beauty and seek to find those in your own lives by whatever ways you seek appropriate, and that the ideas that we've discussed tonight will stay with you for a long time. Thank you, and we look forward to seeing you again at a future event.